Thank you everyone for tuning in. It's my pleasure to introduce Deeksha Shama. Deeksha is a PhD student at the Johns Hopkins University, and she joined us this summer for her internship. Deeksha, we're all ears and brains.
Thank you, Dimitra, for your kind introduction of me. Before diving into the topic, to talk about how brain signals can be employed for informing the actions, let me talk a little more about myself. I am a PhD student at Johns Hopkins University, finishing up my 4th year with a couple of more years to explore and enjoy. I'm advised by Professor Archana Venkatraman. Both of us moved to Boston University with Archana transferring there, and I hold a visiting position at the other university as well. Previously, I was in NITK India doing my bachelor's, also collaborating with Indian Institute of Science and EPFL for a variety of research endeavors. My research interest in core lies around biomedical signal processing and trustworthy machine learning with the applications of computational neuroscience and brain-computer interfaces. Archana's lab is known as Neural System Analysis Laboratory with the main goal of decoding the brain one snapshot at a time, not just for healthy brains, but also for data collected from different populations such as autistic and schizophrenic and epileptic populations. In my free time, I love volunteering. I'm part of a variety of organizations in the community. I'm taking up the position, a board officer position in Women in Medical Imaging community for the next couple of years. And I enjoy doing dance, art, with a couple of my art pieces out there for you to see. And I love hiking, which has been a great thing to do this summer. And I'm not just research, I've had a great deal of fun working with this team and being in Seattle. Having said that, let's dive deeper into how we can employ foundation models for monitoring and explaining cognitive load from the users. In today's talk, I'll set forth the introduction to talk about BCIs and EEG signals that we employ in my study, and structure the proposed pipeline with the machine learning setup and the experimentations that we did, and let you all leave this talk with some results and insights that can be used for the future studies that you have in mind. Brain-computer interfaces has been an active area of research for the past couple of decades. The main goal of this research is to establish a direct connection from the brain to the machine by bypassing the traditional input modalities. Imagine controlling a computer screen, or looking at a computer screen and moving a pointer maybe, or your cursor to take an action. In another example, imagine an assistant tracking your mental state and your well-being to intervene or provide feedback to say, hey, take a break. And I'm sure if you have a watch, it's already telling you to stand up and take a walk around once in a while. BCIs come in varieties. Passive BCIs, where most of the processing is done in the background after collecting the sensor data. Variety of sensors data can be collected either directly from the surface of the brain, eye gaze signals, heart rate signals, and these can be used to infer the state and the action that needs to be taken without requiring the traditional input modalities. In case of active and interactive BCIs, the computer steps in to either give a feedback or take an action to perform the task. In today's talk, we'll focus on cognitive load monitoring, which has immense potential to be employed in variety of tasks. This could be gaming to provide variety of personalized tasks or the levels for the user. Driving to identify when the driver is fatigued, and for the autonomous driving to probably take over and aid in stressful situations. Mental health and stress management and well-being and health in general, which can help in productivity and improving overall life quality. To assess this, we focus the task on personalized learning, which is another avenue where cognitive load monitoring can help. For example, when a person is acquiring a new skill or a child is taking up a new course, what if we can control the course that they're learning from based on how much effort it took in the previous course? If this experience can be personalized, studies have showed that the overall training time and experience improves is faster by about 25%. This can be done with a general schematic looking like this, where a computer accesses signals and your mental state from the physiological signals and computes the effort and the cognitive load it took to complete the particular course, and then inform the next module to be selected based on that. In our setup, we focus on faster pilot training to improve the quality and the experience of learning to fly a plane. And we did this setup in the BCI lab in the Microsoft Redmond 99. To this end, multiple participants came and were plugged in with variety of sensors and did the tasks in a virtual reality setup. So as you see in the left, I'll also play the video of them doing a particular task. They have a VR setup, VR glass setup, and then multiple sensors, including the electrodes in the head scalp, as well as breathing signals on their. Let me get my pointer. Yes, the head scalp, you can see some sensors over here, respiratory belt here to get how heavily they're breathing, along with some sensors in their fingers over here. And during this task, they are required to look into the display on the right and to complete the task at various difficulties. These difficulties of the task is dependent on how clear their visibility is and how much effort it takes for them to do it. And they have control with the throttle in one hand and the speed in the other hand. You can see how intensive this task is. It's visual, it's planning, it's decision, organization. So it's a lot of effort. And our participants went through this from 1 to 5 days, many of them for all 5 days, with the tasks lasting 1 to 2 minutes at a time, and an overall 20 sessions at max, so several hours a day. And they learn this do this for 5 days in total. And when they're going through this, the added difficulty comes from all the sensors that they're plugged in. And one of the goals of the studies would be how much of these sensors are useful and how can we optimize the design of the task in the future studies. Here we focus solely on the signals collected from the head, which is EEG signals. EEG signals look like these wiggly lines on the left. So these are so you can see multiple of these because these are collected from different positions in the scalp. So these are placed in the front of the brain, center of the head, back of the brain, and all of them interplay with each other to give some information, which you probably are not seeing in this signal because it's super hard to infer anything from a signal that's plotted just over time. And that is where we need some help from the computational automated methods to give us information from the signals that look as complicated and are high dimensional like this. However, some effort has already been done in assigning importance to different parts of the regions. So as pointed here, prefrontal cortex, which is in the front of the brain, and frontal lobe, which is in the front top of the head, is quite active in decision making, organization, and to be able to access your memory and pay attention and make decisions. However, since the task we are doing is virtual reality and has a visual component to it, it is expected for the parietal lobe and occipital lobe to be active as well, where the visual information and the spatial awareness is processed. Having said that, EEG signal is only collected on the top of the head, and by the time the electrical activity moves from the cortex, which is deep inside the head, and comes above to the scalp, there's a lot of aggregation and crosstalk that happens, and every signal here has some amount of information collected from other parts of the neighborhood regions as well. And this is why this high correlation that we see in EEG, both in spatial direction and temporal direction, mandates the need for careful handling and meaningful feature extraction with set pipeline. And excellent work has already been done in this area. One of the avenues that has successfully worked for cognitive load monitoring is looking into the power spectral density of the EEG signals in various frequency bands. So the typical frequency regions looked into are called alpha, beta, gamma, theta, and there are 5 frequency, sorry?
Mu, but
Mu.
it's the same as gamma because of the
Yes.
context, motor cortex.
Yes, and these signals are extracted after pre-processing and cutting down the really long EEG signals into tiny temporal windows and processing the time and spatial dimensions, including some feature dimensionality reductions and employing a machine learning model. While this current state of the art has given decent performance, especially improved with additional information from different sensors, the challenge comes in the fact that these are sensitive to the pre-processing steps. It has been noted that with varying temporal window lengths and pre-processing strategies, different tasks benefit differently, and hence it's highly task dependent. The features are not as generic and requires a good amount of effort in identifying this particular aspect. With the amount of dimensionality reduction and the task dependency it exists, there's also limited flexibility in handling the EEG signals, and all of these are things that we would like to address in this internship. And hence, we arrive at the research questions that we asked at the beginning of the internship. Can we leverage pre-trained models that have been trained on extremely humongous amount of data, be leveraged to extract novel features that are generalizable and are more flexible to be employed for the specialized task of cognitive load estimation? What is the best way to handle these features obtained by the models, and how do they compare to the current state of art? The second question is, with increased complexity that comes from the larger models, how meaningful and reliable are these features? And how do we compare it to the conclusions that we have from the neuroscientific study? Can we use this to track progression over days? And can we use this information to design future tasks? That brings us to the concept of brain foundation models. The computational automated methods from EEG signals, it has evolved over years. Initially with traditional methods, has gone to employ machine learning and more complex machine learning models. With increasing complexity came the brain foundation models, which are trained to understand the domain and not the task in specific, and be able to easily adapt to newer tasks. However, as the complexity increased over time, how much of the interpretability are we losing? Can we make this method reliable and comparable to the state of the art that we have? And how can we do this is a question that we would like to answer. The general framework of brain foundation model looks like this. During the development phase of any of these models, they typically take an EEG signal that you see on the left, and they mask certain parts of it and feed it into the model. Typically, the original EEG signals are fed to get the latent representation, and a decoder is used to reconstruct the masked patches. These reconstruction could be autoregressive in nature by looking only at the past, contrastive in the way the loss function is defined, or spatiotemporal in nature, that is to say, the reconstruction could be either of the original EEG signals, which is extremely challenging, or reconstructing the Fourier, the frequency domain of the signal. Once this is fixed, the latent representations are expected to be generalizable and be used for multiple downstream tasks. In our case, the task of cognitive load monitoring. Hence, how do we employ these foundation models for the downstream tasks? Each foundation model is capable of inputting giving a feature, a latent feature for a particular token, and this token is, in terms of EEG, is defined for 1 second from one EEG channel. A channel is the one brain position electrode that we have. So for each input that there are, it's cut into multiple segments, and each of these segments are further cut into a single channel and a single second before feeding it into the model, along with some positional encoding. So all of these multiple tokens go into the model to give us a latent representation. And then we employ a variety of downstream layers to get the cognitive load score. These downstream layers, final prediction layers, are required to process the multiple dimensions and correlations that exist in the EEG data. And we try and experiment with different possible ways of designing this. We had the question of the choice of what's a good encoder that we can employ, what are the different ways we can handle the other dimensions of the features out given by the model. So the first aspect that we experimented with is the BFM encoder, and we started with LaBram and compared it with one other model. LaBram was developed earlier in this year in 2025, and it is a multi-layer transformer model with vector quantized neural tokenizer. It also has a parameterized temporal and spatial positional embedding, quite standard practice, also seen in other domains of data modalities. Here, the input was original EEG signals, which was used to reconstruct the Fourier transform during the pre-training stage. The impressive part is they used 3,000 hours of EEG data for pre-training. To give a perspective, an average EEG data is somewhere between 50 to 100 hours of data, and this is several times that a typical data set. And they experimented with 4 classification tasks. In contrast, the Zebra mod that we had a similar setup. They replaced the traditional transformer with the crisscross attentional transformer to be able to handle different correlations of EEG signals, and also replaced the typical positional encoding with the convolutional layer-based embedding. This reduced the parameter size of the model significantly, but it's also shared across all of the EEG channels to extract the positional encoding. Then the other advancement that the Zebra mod model had is they trained it on 9,000 hours of data sets, which is 20 times an average data set, which is expected to add more information and make the whole model more generalizable. They also experimented on 6 downstream classification tasks and have impressive results in comparison, both comparable to LaBram. Once we selected the foundation models, we identified that each foundation models gives the feature per every token that it has, and we have to make a design choice on how do we extract the information from this large number of features that we have. The first thing to note is the task of cognitive load monitoring in our case is per 1 to 2 minutes. So we would like to first compress the temporal dimensions to not be as dynamic in nature. So the first thing that we do is across the 16-second segments that we have, we average it across the 1 second. So we have final representation out of an encoder is per channel per segment. And then we ask, how do we handle the time across these segments? Can we just take the mean of it and get a good performance, or do we add multiple dimensions and use all of the features that's output by the model per time segment? And then the other dimension that we need to consider is this channel dimension, which is across the brain space. And how do we handle this? Do we take an average, or do we take an intersection and get the final output using different prediction layers that we experimented with? We'll look into the results later. Before that, let's look at the data collection that we had. This was done by the team a couple of years ago. There are 3 major cohorts of data. The main experiments are done with the 16 participants that had 32 electrode system. This had about 70 hours of EEG data, a decent size of which we can use to impart some specialized knowledge of cognitive load task into the foundation models. And then there are a couple of other cohorts of data with slightly smaller duration of EEG. The main thing to note is that they might have some different instrumentation in the data during data collection. Also, the tasks that the participants were requested to do also evolved over time, and the configuration also changed from the config 26 to the main. So this adds a nuance to the variabilities in the dataset that we look into and try and disambiguate the results. The ground truth of cognitive load score that we have is not subjective in nature, and this is a method proposed by the team as well, where the objective score only relies on the performance as well as the experience and the task difficulty the person is going through. This way, we are trying to ensure that the model is not biased by a single participant. on the right, you're looking at the range of the scores that each of the 30 participants we have. At 30 participants that we have, 27 of them were included. We set up our experiments to be in a nested cross-validation setup where we look into the correlation score between the predicted score and the output of the model. And in order to look into the correlation score, we need a large number of samples in the test subject. So we take only last few participants in the test set and choose one of them as the test and one of them as validation and use rest of them in the training. So this setup is our leave one out experimental setup to ensure that we are not overfitting into a particular training set. And we report all the results as correlation in average across the nested cross-validation setup. We also do minimal pre-processing, which is bandpass filter across the entire range of frequencies of interest and resampling it to 200 Hertz to fit the setup that the LabRAM and CBRA models had during their pre-training stage. Now let's look into some exciting results and insights we have. Answering the first question of what would be a good foundation model and what's the good optimized strategy to handle the features, we compare it with the state of the art and some other deep encoders trained from scratch. The state of the art had an impressive result with LSTM with the correlation of up to 0.3 and comparable results with a simple linear layer and deep neural network. In comparison, the encoders that are trained from scratch handle the channels and the temporal dimensions differently. EEG-net is a fully convolutional model, so there's no much flexibility in how we can employ, if we can employ an LSTM in the end. EEG conformer has a convolutional layer and a transformer layer to implicitly handle all the correlations, and thus allowing us to only add a couple of few linear layers in the end to make the prediction. It does improve in case of DNN over the state of the art, but the performance is only comparable to the state of the art. In contrast, the foundation models that we have showed a decent performance improvement over the state of the art, especially with just having a linear layer or a deep neural network which had 2-3 layers during prediction. CBRA is in fact good during SVM, but also in the validation sets of all other prediction layers that we have. This gives me, the takeaway from here is the hyperparameters chosen for CBRA is quite sensitive to the choice of it, and it's hard to generalize to the test set. And this could be because of the kind of positional encoding that they are using. It has weights shared across all the channels and may not be able to separate the different information from all the channels efficiently. LabRAM has pretty good performance and is in par with the state of the art, sometimes even improving on them with just a linear layer. But how did we arrive at this? What are the different ablations that we did to come at this result? The first question was handling the channels. So since we have variable electrode configurations later on, and we would like to have the ability to incorporate data from different channels, one of the options is to take the intersection from the 9 regions of interest. The other option is to take group average of all the electrodes coinciding at the regions of interest. We'll look at the CBRA model first. On the x-axis, you're seeing the different prediction layers that we looked into, and on the y-axis, you're seeing the nested average cross-correlation. In light green is the intersection performance, and in dark green is the group average performance. And in most cases, having group average has a better average performance across the 20 cross-validation setup that we had. And this performance is significantly improves in the LabRAM group average in the dark purple. And this trend is also seen if you handle the time dimension differently. So the takeaway is having group average features, including information from 2-3 electrodes per region, is more informative than sending in just a single channel per region. And this is possible with larger models like this because they are capable of handling up to 128 channels without confusing the final prediction. And the next question, after we selected how to handle the channels, since group average was a clear winner, we asked how could we handle the time dimension in the signal. We could either take the mean, shown in light green, mean and standard deviation shown in sap green, and all of them in dark green. And again, I'm plotting the nested cross average correlation of different configurations. And here there's no clear winner, both in CBRA-mod models and in LabRA models. My suggestion, however, is using mean would be an excellent and an easy choice for simplicity and when you would like to have a direct output quickly. However, using all of them gives more flexibility on how to handle all of these features. And with more complex models and with more data, we would be able to benefit from having all the features fed into the model and learning directly from them. The caveat being that when you're using all of them, we have to fix the dimensions, so either zero padding or cropping may be necessary. The next thing that we experimented with, how does adding more cohorts affect? So in the data slide, I showed that we had a couple of other cohorts with variable channel configurations and possibly different instrumentation during data collection. So the question we asked is, how does adding these increased variability into the training data set affect the model? And these variabilities, in addition to coming from instrumentation and the data collection, also comes from the subject variability and the state of mind the person is during the task. And thus, it could make or break the model during training. And what we observed is adding more data across time, adding more data on the x-axis does in fact improve the nested average correlation. This implies that both LabRAM and CBRA-mod model, LabRAM specifically, is able to extract meaningful information from it and not relying on confounding factors, and are able to identify the patterns that are specialized for cognitive load. And to ascertain this further, we conduct some explainability tests. These tests are necessary and are not seen as often in the literature, particularly for EEG studies. The nature of EEG being wonderfully challenging with so many correlations, it's harder to ascertain what the model is picking up on, and with the increased complexity of the model, with their black box nature, it's really difficult to ground this result into the information that we have from neuroscience. Thus, we establish an experimental protocol and conduct some explainability tests. For this, to this end, we answer the question of why do we have better performance with certain models by tying these into feature importance using partition SHAP analysis. We included partition SHAP because it is a paradigm that involves a game theoretic approach while considering the various conditional dependencies in the EEG signals, that be it anatomical, be it temporal. And doing that, we construct a hierarchical tree graph, and the method goes ahead and perturbs each of the EEG inputs and assesses how the output of the model changes depending on the perturbation. Intuitively, you can think of it as an electrode losing contact with the head and it being just noise. Or at a certain time point, artifacts take over more. Artifacts, by artifacts, I mean hand-eye movements or muscle movements, and the brain effort that goes into making these movements affecting the output more, influencing the output. So these perturbations can be thought of as do exist significantly in EEG signals as well. And then we obtain some averaging per channels for local explanations and across test sets for global explanations. Here's one plot from one of our global explanations from the CBRA-mod model. So this circular plot is a topological head plot. The front is pointed by the triangle, and the ears are pointed to the left and right side of the head. What we observed here, and although I'm showing deep neural network here, we saw the same trend across different prediction layers that we had, is that CBRA-mod model relies more on the back of the brain. And why is this doing this? This is possibly because of the visual nature of the task and the spatial awareness. It's picking up on the features from there. However, in contrast, LabRAM has lower importance to the back of the head and more importance to the front of the head. And this aligns perfectly with the knowledge that we have from the neuroscience studies by the neuroscience population. And this could also correlate the increased performance that we saw with labrum in contrast to zebra mod. The next thing that we explored, which I haven't really touched upon until now while we were taking average of performance for participants, is the fact that participants came for multiple days. They started learning the task of pilot training on day 0 to day 5, and how does this change over days. And we saw that with labrum model that the importance of the prefrontal and frontal region in fact increases over days. And this could indicate that the person is learning more and their front of the brain is more activated, where the working memory and decision and planning exists. To ascertain this, we looked into the other modalities of signals that we had, one of them being the gaze feature. So on the bottom left, I'm plotting the variety of gaze features, average over days, day 0 to day 5 days. So if you look into the blink rate and the pupil dilation, average pupil ratio, pupil to iris ratio, they in red and blue, it's not changing as much. However, if you look into the blink duration and the focus stability, it reduces after day 1. The focus reduces after day 1, whereas the blink duration increases over days. So what's happening is all the 5 test participants on average are blinking for longer, and their focus is not that high. So they are getting more relaxed, whereas in the earlier days, they are concentrated, they're locked in, and they're trying their best to learn from it, and their effort is much higher in the earlier days. And this is also indicated in the ground truth cognitive score in purple here. As you can see, the average score of ground truth cognitive load, in fact, decreases after day 1. And this possibly correlates with the prefrontal importance that's increasing over days. The front of the brain is more active, and the labrum model is picking up on it and improving its own performance, plotted in pink here. So how can we use this information? So it's becoming more evident that there is a good correlation between the front of the brain, which has been established by other studies as well. So some of the things this conclusion can be used in optimizing the study. If it is the cognitive load score that someone is interested in tracking, the visual nature of a task is harder to disambiguate. There are several confounding factors that the visual task would enter, and to remove this factor, it may be a good idea to look into front of the brain by either changing the data acquisition protocol or changing the architecture such that the attention to the front of the brain is higher in the deep learning model that we have. A quick message that I would like to put forth before concluding the talk is the implementation perspective. Yes, the parameter space has increased. There are about 5 million parameters and 6 million parameters in each both zebra mod and labrum respectively. And the additional parameters come from the low rank layers that we have, about 18,000 and 300,000 parameters in each of them. How does it affect the end-to-end processing? By end-to-end, I mean pre-processing to feature extraction to prediction of the final cognitive score, minus the data loading itself. And we see that all of these methods are in fact less than a second, and a zebra mod being much faster due to the shared weights and lesser number of parameters that it has. And this is for 1 to 2 minute EEG recordings that we have. Thus, this method still maintains the potential for real-time application and can be employed for a variety of tasks. So to summarize the contributions from this internship, as we have successfully adapted 2 foundation models for the task of cognitive load monitoring. We identified and designed the best model configuration, giving performance on par with the state of the art. We also identified that group channel features are more informative than having a single channel, and while the temporal aggregation may or may not retain the entire diversity of features. We also mapped feature importance locally and globally in an effort to identify the optimal configuration for current and future studies, and also disambiguate biases in the model. And these contributions have made way for several future avenues, unlocking the ability to provide adaptive content delivery, for example, in games, game levels, or movies, or training modules, in addition to multisensory stimulations in identifying the optimal design for a variety of these content delivery. We could also identify driver fatigue during experiments and monitor well-being of variety of users. And with that, I conclude my talk. Thank you everyone for listening. Thank you audio team for an exciting summer and a holistic teaching environment. Thank you to the entire population of MSR interns. We have had so much fun in variety of events conducted by the intern team. They have had an excellent organizing protocol as well. And Microsoft for having me for the summer. And questions and feedback, most welcome. Yes?
Actually, go back to slide 20.
Is there a faster way to do this?
Yeah, exit for.
Okay. So LSTM, upper right corner, 0.2. Where did you get that number?
From the previous publication from the team.
My paper?
Yes.
That number is fishy, honestly. Overall, I see that you exceeded the state-of-the-art results. That LSTM, I think there is a bug in the implementation of LSTM in MATLAB.
Yeah.
And we didn't trust, and even we recommended using DNN,
Okay.
regardless of that difference.
Okay. Yeah, LSTMs are usually harder to train. Even with these features, I would suggest looking into deep neural network or LSTM, a single linear layer. It gets harder to train LSTMs on smaller data
What is
sets.
the difference between one layer DNN and DNN?
This is a simple linear regression model. I added some regularization because the number of features that we have is huge. In deep neural network, we have, instead of regularization using L1 and L2 penalty, I use batch norm layers and add multiple neural network layers.
How many layers you have in the
Two.
DNN? 2 layers.
Yes. One for the channel, one for the time.
Okay.
So the metric is correlation coefficient?
Yes. Because we need a large number of participants to ensure there are no spurious correlations, we have certain steps to ensure that doesn't happen.
I had one thought on the, with EEG, I guess there's a lot of variability in terms of the setup, right? I was wondering if you could see if there was a way to check whether the representation of the data set, your data set that you train on, versus some of the data sets that these models were either trained or tested on, if there's maybe a distribution shift, either in the embedding space, or I'm assuming these models are trained as encoder-decoder.
Yeah.
What would happen if you try to reproduce your signals versus the test signals, and is there a shift in?
I see. I have not tried reconstruction exactly, but I've looked into the embeddings output by the model. So I did some cluster plots, although not all of them together, because it would clearly make two clusters of one data set and the other data set. But I plotted them separately, and what I identified is the clustering depends on the participant more than the data set. And the clustering also depends on the particular day it was trained, it was collected from. And there's a clear trajectory of the encodings over time. It can track the temporal similarities. So I would expect it to see the differences in two data sets, but also the difference in two participants and the days the data was collected.
And was there a difference between the two models or similar?
The conclusions were similar, but I didn't look at all of the features at the same time. Yeah.
I guess my question is whether you could, like, from that somehow gauge which model might do better or which model might need more fine-tuning potentially to account for a distribution shift.
No, I think representations looked similar. It's more the temporal similarity and I didn't look at the spatial differences, but the temporal similarities affected a lot for the representation.
Okay. Yeah. Thank you.
Can you go a few slides forward? There's this picture of,
Head?
yes. Yes, how do you interpret this?
Yes. So the tiny dots are not so clear, but if you can see them, that's where the electrodes are placed. And the red color means that the features of that region had higher influence in the final output of the model. So EEG signals that were collected from this region affected the output a lot.
So dark blue means it's
Not so much.
So how come the two models have this contrast between the top region?
Yeah, I think once the features are fed into the model, there's a attention looks into all of the channels. There's a self-attention that goes through it, and there's a lot of feature interplay happening within the model. And once the entire pipeline is gone through, it appears that the labrum plus downstream layers depends on the features from the front of the region more than in CBRA-mod. It looks into the back of the region to make the predictions. So we do not have control on what weights are assigned to all of them. The model's trained and finds the optimal point, and it appears that labrum with improved performance in fact looked into the front of the brain.
I guess related to that question I see here, if my eyes don't betray me, there's only, the back region is actually pretty sparsely populated with electrodes, right?
Yeah.
So the visualization also might play some tricks here.
Yeah, it's interpolated to plot it across the head.
Yeah.
So just to perform so both model, they are like transformer, like encoder model trained on the mass prediction, right? So the biggest difference is the training data, or the size of the training data.
Training data, positional encodings are different as well, and the self-attention is slightly computed differently in the two models. So if I go back a few slides. Yeah. So the CBRA-mod proposed something called crisscross attentional transformer. So the way the self-attention, the matrix transformation is subsampled and then averaged over different subsampled attention values.
Okay, but the still apply like in the time axis, right?
And channel axis.
Yeah, so in the time channel instead of like across all the channel electrodes of the EEG.
Both. It's across the electrodes of the EEG.
You mean like across like both dimensions? They have like attention across the time, the attention across
the crisscross
channel,
attention
across the
has
electrodes.
both across time and channel, whereas the transformer here, they have a temporal transformer and a spatial transformer separately done.
Yeah, so basically you think like the difference of the brain map region is probably maybe due to the architecture?
It's more than attention. I think it's the way the positional encodings are computed, so they are directly added to the features. And the labrum looks into all of, clearly differentiates each of the electrode positions. They have about 150 positional encodings to assign positions to all of them. Whereas CBRA-mod is using a convolutional parameter, so it doesn't really matter in what order you give the input to CBRA-mod. It's going to employ the same convolutional filters with assumptions of neighborhood similarity to derive the features.
Yeah.
Go ahead. What is the model size of these? What is the size of these models?
labrum encoder has about 6 million parameters. CBRA-mod has 5 million parameters.
Okay, so is it possible to inference in real time?
Yes, I saw it just with the CPU. I could do it in less than a second. Yeah.
Another question is both models evaluate on multiple tasks, where you just are doing some filter on only one specific task.
Can you say that again?
Yeah. Both models are pre-trained and applied to multiple tasks, like usually is one for 4 tasks, another for 6 tasks.
Yeah.
So why you only apply those models to one specific task?
The difference between our task and these tasks are they are classification tasks, and we were focused on the regression task of cognitive load. And we were interested more in also disambiguating what the features are actually looking into. So once we decided on the task, we looked into more answering the more explainability based questions. And the regression task is quite different from what they have worked on, and it was harder to find the best configuration, and it took a while to find the best optimal design as well.
Plus the training has nothing to do with the tasks. So they train the foundation model, they get the latent space representation and try to build some small classifier on top of that for, usually it's a motion detection, they have several labeled corpuses. In this case, it's just another, to think about this as a fifth or seventh task, which we investigate, can this latent space representation still preserve the information about the workload. But the task they did not participate into the training of the foundation model in any way.
Oh, yes, so I think that so there are some study, especially for this kind of first kind of the model that shows if you want to do sub-probing, the best embedding is not the last layer embedding. It's in the third quarter of the model. So if there are 12 layers, the best feature actually came from 8 or 9 layers instead of the last one. So right now you're just using the last layer.
Yeah, that's an excellent idea. Not including all of the 12 layers, and maybe there's more information.
Because I think the reason is that for this kind of the SSL, the last layer is optimized for that SSL objective specifically, right?
Yeah.
So basically, the last embedding is overfitting to the mass token prediction. So the feature before that is actually better than the last one. So
That's a great point. That would be a great thing to experiment with as well. Yeah, there are multiple layers in this model. There are about 12 transformer layers, and there is a possibility that the best,
One of the empirical results is using the weighted sum of all layers, where the weight can be learned during your machine learning.
Can you say that a little louder, please?
One of the alternations is to use the weighted sum of all the feature of all layers, and the weight can be learned during the fine tuning. And that typically maybe not give you the best result, but it's quite similar compared to the best specific layers among the 12 layers also.
My question is the goal by adding output from multiple layers is to ensure more harmony of features? What's the advantage of doing that?
Not addition, it is some kind of you adding one convolution layer among all layers, so the result will be some kind of ensemble of all layers.
I see. Okay.
I'm not sure if I understood it right, but as I understood it, you did an experiment with grouping channels, right?
Yeah.
But you also said that models can take up to 128 channels. So does that mean that grouping several channels to region that improve the robustness rather than feeding them separately?
So let me clarify. In the beginning, all the channels are fed in separately, and the features output by the models are grouped together. This is because in the temporal domain, they can cancel each other, and if you group them in the beginning, it cancels it out. So plus, minus, it's different polarities. So it's not suggested to do that in the beginning. So you group the features in the end. So the model still gets to see all of the features, all of the EEG features.
And you did some kind of superficial evaluation of the features from the gaze tracker. Did you have time to train a classifier and to let the neural network see which are important, which are not, and just to compare, and to, more importantly, actually to do the late fusion between the EEG and the gaze tracker features?
I tried training a model. It gave just with eye gaze features, it gave performance on par with the EEG performance that we have here, but I didn't probe into what's important and what's not important. And it might turn out that the trends that we saw, those features would come out as more important in prediction.
Our previous study showed that.
Okay.
Can you go back to the topological map? Right here. Question number one. It is such a clear picture, the front and the back, and a great explanation. Maybe the task is visual. You get here in the back, and it involves cognitive load, so you get something in the front. Have you checked if the rest of the signals were actually useful? Was it just noise, or were there actual present? Question number one.
Yes, these are averaged outputs. So for different inputs, it would change a little. And I would expect some influence from all of these signals, given the locations that they are in. They do have some information in terms of movements or decision making or handedness, for example. On average, the contribution is not as high. So if we completely leave them out, we might lose some performance. But there may be a way, in a smart way, to have a weighted average or in the input or in the feature space that can help us improve the performance.
And question number two, does that say anything about the task that the participants were involved in? If we're looking for cognitive load, is it advised to have a visual task that may take away brain power, basically processing power, if we want to really actually measure cognitive load and focus on just that? Is that just a way to, this visualization, this kind of visualization, a way to help you understand which task may be more appropriate for measuring cognitive load?
From a science perspective, to isolate the value of cognitive load, it may be better to design experiments that are more mental in nature, maybe adding or talking or listening to different sources. And this may give us better idea. But from an implementation perspective, if you think of a product or a tool, it's harder to define what the person's doing a task. For example, if we are thinking about driving or gaming or the content delivery, the visual aspect is always going to stay. So it may be more prudent to change the way we compute the cognitive load by adding more attention and influencing teaching the model to look in the front of the brain rather than changing the task that they're doing itself.
I'm surprised to see that the back, where the visual cortex is, has a value at all. But in the light of what Dimitra said, the task is heavy visually.
Yeah.
But the visual load is relatively the same. And maybe the neural network uses it as a reference and based on that estimates how much more or less load we have in the frontal cortex, where presumably the cognitive load is supposed to be.
Yeah. Yeah, that's my take from these plots as well. Any other questions?
Any other questions online? Feel free. I'll give you a couple of seconds. All right, let's thank Deeksha.
Thank you, everyone.